we continue with decimal for fractions. We learned earlier that for 1 over n, it could be pure recurrent decimal if n does not have any prime factor 2 or 5. Now in this case, I have 1 over 109, the period length is really long, versus a bigger prime number, 137, 1 over 37 has much shorter period length. So what's going on here? We're going to learn that today. Now recall that for general fraction m over n, we assume mn are co-prime and m is smaller. So this fraction is always less than 1. There are 3 cases, that is, depending on the denominator n. So if n has pure 2 or 5 prime factors with their powers, then it would be a terminating decimal. That is, the decimal digits are finite. Now, on the other hand, if you do not have any 2 or 5, that is, the GCD of n and 10 is 1. They're co-prime. In that case, it would be pure recurrent decimal. Now, for the third case, that is mixed. That is, you have both 2 and 5 and non-2 or 5 prime factors. Then we would have a mixed recurrent decimals. Today, we're going to focus on case number 2. Now, what is the period length? We're going to start with some examples. Here I have 1 over n from 70 to 99. Notice I highlighted here 79. Yeah, that has 13 period length. And 97, it has 96, a really long one, right? So that's just not consistent, right, with the n value. So let's study what's going on here with another example. Here we're going to try, so when we're the decimal first repeat, then we will know what the period length, right? We're going to start with a typical long division if we try to figure out 1 over n, right? For example, 1 over 37, we know that it is period length 3, that is 0 to 7 repeating, 0 to 7, 0 to 7. And the way we do it with long division, you're going to start, then you have to put 2 zeros, right? And then you get 2. The remainder here is going to be 26. Yeah, this is the remainder. And then you're going to append another 0 here and continue with the process, and you're going to 7. And here you get remainder 1. So when you have 1, you're going to repeat, right? Since we're dealing with what is called the pure recurrent decimal, and we always start with 1 because we're only considering the fraction. Numerator is 1 over n, right? So the answer to the question, when will the digit repeat? It will repeat when we have the remainder 1 in the long division process, right? And that will now guarantee to happen. Okay, so here we notice that in this case, since 1 appear here, we're going to restart from 0. So the period length would be 0 to 7. So what we have here is really, we have 1000, right? So mathematically, the equation would be 1000 equals 37 times 27 plus 1. In other words, when the divisor is 37, so we have 10 to the third power is congruent to 1 when we consider mod 37. And then when that happens, 3 would be the period length, 0 to 7, right? So that is the pattern we learn, from this example, right? So when we come back to the question, when will the decimal first repeat? The answer is going to repeat when you get remainder 1 in the process. Mathematically, we are looking for something 10 to some power is congruent to 1 with the modulus 37, right? So how about general n, 1 over n? Again, we're looking for something that is 10 to some power is congruent to 1 with mod n. So we need the first occurrence of that is smallest integer k, such that this happens. Alright. So with that, a related theorem on this is what is called Euler theorem, that says when we have a and n co-prime here, and a raised to some power is going to be congruent to 1 mod n. Now that is something here is called Euler's Totient function. We call it phi of n. It counts the integers from 1 to n, that is co-prime to n. Alright, so it's very useful in a lot of number theory problems. So in our case, we know that we're looking for, 10 raised to some power is congruent to 1 mod n, right? Now we're going to start with some examples of Euler's Totient function, right? So in the case where we have pure recurrent decimal, n and 10 would be co-prime, right? So 10 would be a here, right? The number a here. So we're looking for 10 raised to the k's power congruent to 1. But we know for sure that 10 raised to phi n is going to be, according to Euler theorem, is going to be congruent to 1. Yeah. So let's start with some examples for the phi of n. Now, if n is a prime number, yeah, we know that all the numbers smaller than it is going to be relative prime to it, because prime number doesn't have any factors other than number 1 and itself. So the total number that is co-prime to a number p is going to be p minus 1. Okay. So how about the power of prime numbers, like p raised to the r's power, where r is a positive integer? Then we're going to exclude all the prime factor of p, the total p raised to r divided by p, right? So this is a formula here for the power of primes. Now how about some real example here, right? 7 would be 6, and 17, a prime number, that would be 16. How about 17 square? That would be 17 times 16, that would be 272, right? So that's just for the prime numbers. Now for any other numbers, we're not going to derive the steps, but here we just take it as a conclusion that if you have the prime factorization of n, then the phi function, the Euler's Totient function, can be calculated by the prime factors, the p1 through pk, with this formula here. Now for example, 21 is 3 times 7, so you plug in the number here, phi of 21 is going to be 12. Alright, so that's Euler's phi function, right? Now let's go back to the original question. When will the decimal first repeat? From earlier analysis, we know that we're looking for a smallest integer k, so that 10 raised to k's power is congruent to 1 mod n. Yeah, so we're looking for k here. Yeah, and we know for sure the phi of n satisfies this. So k would be something either equal to phi n or smaller than that. Yeah, so because since in the worst case I could have phi of n, right? For example, earlier prime number 7, the phi 7 is 6. We know that 1 over 7 indeed has pure length of 6, right? So now we claim that not only k is smaller than phi n, but also k is a factor of phi n. That is, we know for sure k cannot be exceeding phi n because we're looking for smallest integer k, right? We also claim that k divides phi of n. We need to prove that. The smallest integer must divide phi of n, right? So here we're looking for smallest integer k, right? So how do we prove that? That can be proved by, what is called the proof-by-contradiction, right? So here we want to show that this k we're looking for not only smaller than phi n, but also divides phi n, right? This is through by proof-by-contradiction. So if we assume it does not divide phi n, then we can do the modulus and then we figured out that phi n in that case can be expressed in kq with some quotient plus r. Since phi n is not divisible by k, then the remainder is non-zero. That is, the remainder is going to be smaller than k, but it's greater than 0, does not equal to 0. Alright, so notice that then 10 raised to phi n is going to equal to this expression here. We know that 10 to the k, we assume that's congruent to 1 mod n. And 10 phi n by the Euler theorem is also congruent to 1, right? So what do we conclude? In that case, 10 to the r has to be congruent to 1 mod n. Yeah, but then that means r is an even smaller number than k, that is congruent to 1. But we claim that k is the smallest integer. So this would be a contradiction because r cannot be even smaller than k because we assume k is the smallest integer that satisfies this equation here. Alright, so a contradiction is given here, so which means the original assumption that is false, right? So that is called proof by contradiction. Okay, so we go back to the question. Now we know that we're looking for k. K is going to be a factor of phi n. Okay, so that's our conclusion here. The smallest integer k, and k must divide phi n. What is phi n? We know the answer earlier, right? Let's go back on the example here. So 1 over 79. Earlier we know that phi 79, because 79 is a prime number, equals 78. And the k here is indeed a factor of 78 because k equals 13. 13 is a factor of 38. Yeah. In this case, 1 over 97, k is actually equal to phi, right? So equal to 96. It's a really long one, right? So it really depends. Now there's no rule to tell, if it takes either, directly phi of n or some factor of phi of n. Okay, so there's no good way of attending that. Now, this is just a recap of 1 over 79, yeah, because phi is 78. And then we're looking for smallest k from the factors here, right? We're going to try one by one, And when k equal to 1, the modulus is 10, right? Congruent to 10. When it's 2 is 21, 3 is 52, 6 and 18, 13. Oh, we got it, right? So it's because we try all the factors, because we know k is a factor, but then 10 to the k has congruent to 1, right? So we know that the pure length is going to be 13 in this case. Alright, so for another example, we are celebrating year 2023 now. So what is phi of 2023? Because the factor is 7 times 17 squared. So by the Euler's Totient function formula here, it's going to be 1632. So we know that the pure length of 1 over 2023 is going to be a factor of 1632. Now we're going to try that, and then eventually we figured out that only when k equal 8, 16 is going to be congruent to 1. That's a really long period, right? So 1 over 2023 would have pure recurrent decimal with pure length of 8, 16. Okay, so in this case k equal 8, 16. Okay, of course you can use non-division to figure out what those 8, 16 digits. Check out my other YouTube video for information on that. Okay, so hope you enjoyed the video today, and we're going to have a follow-up video on the subject with some examples as an exercise perhaps. Alright, please like, share and subscribe to the channel.